Okay, so this one is pH. And hopefully you've heard of pH before, but now you'll learn a little bit more about it. First, we'll learn what pH is, why it's important, and then how to monitor it. So in order to understand pH, we first have to look at individual atoms and understand what's going on with individual atoms. Atoms are made up of three components. Now, I'm not talking about large hadron collider stuff with quarks and gluons and everything else, but the largest basic components of an atom are protons, electrons, and neutrons, with the protons and the neutrons being the components that make up the nucleus of an atom and also providing the vast majority of the mass of the atom. So if we look on the bottom, we have a carbon atom. We know we are carbon-based life forms. In a carbon atom, a typical carbon atom, we have 6 protons and 6 neutrons for a total atomic mass of 12. And surrounding that are 6 electrons in orbit. And for a stable non-ionic atom with equal charges, we have 6 protons, or 6 positive charges in the nucleus, and 6 negative charges surrounding as electrons. The simplest of all atoms is a hydrogen atom. It is just 1 proton surrounded by 1 electron. Now, hydrogen does not exist in this form. A single hydrogen atom containing a proton and a neutron is so highly reactive, it would never exist like this. It would react with something else immediately. Hydrogen gas is actually H2, 2 of these coming together and sharing 2 electrons. But the atom itself is just 1 proton, 1 electron. So we're going to skip that for a second and look at something more complicated. Water. Water is 2 hydrogens bound to 1 oxygen. And you'll notice here it is at an angle. It is not straight across with 1 hydrogen on either side. This makes water polar because the hydrogens only have 1 proton in the nucleus. The oxygen has 8 protons in the nucleus. So there's a total of 10 protons in this entire water molecule, and a water molecule that has all its electrons would have 10 electrons orbiting it. 10 protons, 8 over here on the oxygen, 1 on each hydrogen for a total of 10 with 10 electrons orbiting. But because the oxygen is so much larger with 8 protons, it has a stronger pull on those electrons orbiting. So the electrons tend to orbit nearer to the oxygen than you would expect just on average if they were orbiting in a stable pattern. You would expect the electrons to be evenly distributed around this water. That's not the case. They are orbiting the entire thing, but they tend to orbit nearer the water more, or the oxygen end of the water more. And what this ends up in is, since I have more electrons orbiting over here, I end up with a slightly negative charge. I have a little excess of electrons on the oxygen end. So I have a little bit of a negative charge hanging out here near this oxygen. And then the hydrogens, well, they've lost their electron, sort of. They've lost it partially. It still comes over here in orbits, but not as often as it would if the hydrogen was by itself or as just H2. That O is stealing a little bit of those electron orbits. And so these hydrogen positive charges of the protons are slightly exposed, giving you a positive charge on this side. So water is polar with a little bit of a positive charge due to these slightly exposed hydrogens and a slightly negative charge because of the oxygen attracting the negative electrons, all right? Water is a very stable molecule, but it's not completely stable. In a glass of water, there's trillions of trillions of trillions of atoms and molecules of water. And even though most of them are H2O with 10 electrons, some of them ionize due to just random energy in the environment. They will ionize or split and form a hydroxide ion plus a hydrogen ion. Now, I've got a positive and a negative ion. The hydrogen ion is positive. What is a proton? Just one positive charge. So a hydrogen ion is nothing more than an escaped proton. So when water ionizes, what we're really saying is one of the hydrogen protons has escaped without its electron. And that does happen. And it happens quite a bit. It's happening all the time. Just in a glass of water, as a percentage, it's very, very, very low. But because there's so many numbers, there's actually, it's going on all the time. Now, if a hydroxide and a hydrogen bump into each other, you can see from right to left, there's a much bolder arrow pointing back towards water. If hydroxide and hydrogen bump into each other, they will turn right back into water. So it's a reaction that goes both ways. It'll ionize from water into hydroxide and hydrogen. If hydroxide and hydrogen bump into each other, they'll turn right back into water. Now the arrow pointing from right to left, hydroxide and hydrogen turning back into water, is bolder because that's the more stable or preferred direction of this reaction. But it's not just water that ionizes. Lots and lots and lots of substances will do this. They will ionize or split into ions in nature. It happens all the time. It's not a biological process necessarily. It does happen in biological organisms, but it also happens in just inorganic environmental situations all the time. So that's a little bit of background that will help you understand what's coming here for pH. pH literally means potential hydrogen, or it can be talked about as the hydrogen ion activity. The hydrogen ion activity is the acid forming activity in a water solution. And we don't literally call it the hydrogen ion concentration because technically it's a little more complicated than that. It's more than just how many hydrogen ions are there. It's the activity level of those hydrogen ions, which can be influenced by other factors, including the presence of aluminum ions and other things. It gets pretty complicated. But for the most part, we could think of it as the concentration of these hydrogen ions. That's the primary component. Even though it technically is potential hydrogen, activity of the hydrogen, we really are looking at the effective concentration of hydrogen ions. And what did we learn in the previous slides? What is a hydrogen ion? Well, a hydrogen atom is one proton with one electron. The ion has lost its electron. So it's just a proton, a free proton. They're the same thing. A hydrogen ion is nothing more than a free escaped proton. That's all it is. Happens all the time. We have special processes in our bodies. We have things called proton pumps. What is a proton? A hydrogen ion. What is a proton pump? It is a special set of cells in the tissues in your digestive system. Their sole purpose is to pump out these hydrogen ions or protons into the fluid, the stomach acids, and create hydrochloric acid in your stomach to help you digest your food. Proton pumps. So it's really easy to create these hydrogen ions. You might recall from photosynthesis. What is happening? Water's being split, the hydrogen's being taken to create these hydrogen ion gradients to help with the chemical reactions that drive photosynthesis. Again, hydrogen ions are very important. And the more hydrogen ions you have, the more acidic, the more acid a solution is. We can also express pH mathematically. So here we have an equation. The pH equals the negative log base 10 of the hydrogen ion concentration. Now these square brackets on either side of the hydrogen ion here, H plus or proton, square brackets in chemistry just mean the concentration of whatever's inside. So square brackets in chemistry are just saying the concentration of. Okay? So the concentration of hydrogen ions times this negative log base 10. What the heck is the negative log? Well, a log is an exponential function, something like we should all understand in California, the Richter scale. The Richter scale, like the pH scale, changes by a factor of 10, a log base 10, for every number in the Richter scale. So if you hear about an earthquake and it was a 2, well, that's 10 times as much energy was released as a 1. But you're still not talking very much. You're lucky if you feel a 2. A 3, you probably felt it, but not much, just a little, whoa, did you feel that? That's 10 times a 2, 10 times more energy than a 2, or 100 times a 1. A 4 is 1,000 times a 1, 100 times a 2, 10 times a 3. Again, each step you're going up by a power of 10. But even a 4 is just, wow, that was fun. It's not till you get to 5s and 6s where you have a real earthquake, at least from our human perspective. You know, a 5 and things start breaking, maybe dishes fall off a shelf or something, picture falls off the wall. 6s, things start getting damaged and maybe somebody gets hurt. 7s is when you're hopefully safe. You know, people start dying when you start hitting the 7s, because each time you go up from a 4 to a 5 to a 6 to a 7, every step is multiplied by 10. And that's a logarithmic scale or an exponential scale. The pH scale is the same exact thing. It goes up from each pH from 0 to 14. Every step from 0 to 1 to 2 to 3 to 4, every step is a 10 times difference or 10-fold difference in the hydrogen ion concentration. But it's a negative log because every step you go up in the pH scale from 1 to 2 to 3, you're going down 10 times in the hydrogen ion concentration. So at a pH of 0, you've got massive amounts of hydrogen ion concentration. It is the most concentrated hydrogen ions you can have in a water solution, pH 0. pH 14 is the lowest possible hydrogen ion concentration. And it's 10 times negative 14, or 1 over 10 to the 14th power. Less concentrated hydrogen ions. It's massive. And I'll show you that in a moment. So the pH scale is logarithmic. A difference of 1 unit represents a 10-fold change in the hydrogen ion concentration. So here, we can see a typical pH scale. And that's not going to help me there. Just move it over here. I don't know if you can see the toolbar. Anyway, you might not be seeing what I'm trying to move around, but you can see the pH down the middle. pH 0 is pure hydrochloric acid, absolutely concentrated, saturated hydrochloric acid solution is pH 0 or 10 to the 0 power. And if you've never heard this before, any number to the 0 power equals 1. So 10 to the 0 power is 1, or 1 pure solution of the most concentrated hydrogen ions that's possible. And then we go to pH 1, pH 2. As we're going down, the number's getting higher. Why? We're going down in the hydrogen ion concentration, up in the pH value. So something like pH 2, well, that's in the general range of stomach acid. 2 point something, it'll be lemon juice. Other acids that we're familiar with, vinegar rather, cola and beer, those are pretty acidic. Tomatoes in the 4.5 range. Coffee is also acidic. And rainwater. Rainwater is 5 point something. Why? I'll talk about it in a little bit. There's actually acids in our atmosphere that form when they dissolve in water. And so rain is normally slightly acidic. Unlike acid rain, which is very acidic, caused by either volcanic activity or industrial pollution that puts large amounts of nitric or sulfuric acid into the air, causing extremely acidic water. But even without volcanoes or industry problems, you do have a normal, clean, natural, beautiful, pure rainy day is slightly acidic. So let's look at something like lemon juice, 10 to the negative 2. What does that mean? 10 to the negative 2 is, what's 10 to the 2? 10 squared is 100. So to the negative 2 is 1 over 100, or 1/100th. All right? So pH 1 is 10 to the negative 1, or 1/10. 10 to the negative 2 is 1/100th. 10 to the negative 3 is 1/1000th. So the concentration of acid in a typical cola is roughly 1,000 times less concentrated, or 1/1000th as concentrated as pure hydrochloric acid. Now, the danger of the acid isn't necessarily the same thing as the pH. So something like lemon juice, is that dangerous? No, it's actually something we add to our food. We love it. Some people like to bite right into lemons. It's not good for your tooth enamel to be chewing on lemons too often, but it's certainly not something that's dangerous. But there are certain acids that could be very dangerous, even less acid than pH 2. And I'll show you some other examples on the other end of the scale. So these are the acids, acidic solutions, going all the way up to just below pH 7. And at pH 7, we have what's considered neutral. We have a balance, a neutral pH, where the OHs, the hydroxides, and the Hs, the hydrogen ions, are in relative balance in the solution. Neutral pH, pH 7. Now, pure water is pH 7. But pure water doesn't exist in nature, and so most water in nature is either slightly acid, like rainwater. What we would call sweet water is slightly acidic. Fresh water, slightly acidic in nature. And then seawater is on the other side of pH 7, where we have, because of all of the salts from the crust of the earth, seawater tends to be a little bit above pH 7, somewhere closer to pH 8, and seawater can vary dramatically depending on where you are. but it's, well, I shouldn't say dramatically, but it can vary quite a bit. If it's landlocked, like Salton Sea, Great Salt Lake, Dead Sea in the Middle East, things like that, yeah, it can vary quite dramatically. But the oceans of the world tend to be within a relatively modest range of each other. But they are alkaline or basic. Now, I prefer the word basic. It is more appropriate for science. And the word alkaline, even though it's technically a valid word, it is easily confused with a term called alkalinity. And alkalinity refers to the resistance or buffering capacity of a pH, which we'll get to in a little bit. So I prefer the term basic solutions. We have acid on the top, bases or basic solutions on the bottom of the chart on your screen here. And if we look at some of these, something like milk of magnesia. Milk of magnesia is something that helps with a sour stomach. Something that you might have, if you have acid indigestion, you could take milk of magnesia, which is a base which helps settle a stomach if you have too much stomach acid and you have heartburn. So milk of magnesia goes by different brand names of products that contain milk of magnesia, or, you know, if you're more old-fashioned, you might be familiar with the milk of magnesia product itself. But that's perfectly healthy to drink as something to settle your stomach. Just a tiny bit more basic than that is household ammonia. Don't drink ammonia. That's going to kill you. So again, just because something has a similar pH does not have any distinctive or definitive relationship to how toxic it is or is not. All right. Oven cleaner, very, very basic. And the most basic of all, pure saturated sodium hydroxide solution. So what is an acid? An acid is any material that will dissolve or dissociate, come apart in water in a way that will increase the hydrogen ion concentration. It's increasing the hydrogen ion concentration, that's it. A base, on the other hand, is any substance that will combine with hydrogen or dissociate to create hydroxides. And what happens when you create hydroxides and they bump into hydrogen? They just become water. So effectively, when you increase hydroxides, you're essentially taking out hydrogens, because the hydrogens, when they bump into hydroxide, turn back into water. So that is what an acid and a base is. So next we'll talk about the importance of soil pH, but I'll take a quick break here at the moment.